All right, class. My mouth is feeling a lot better today. I appreciate your patience yesterday in class. You guys did such good work. I think the biggest mistake is I should have just given you guys the eigenvectors and eigenvalues at the beginning so we could get to the more important stuff at the end. But it's good practice for the exam coming up, I guess. So just really quick, you guys did really well at the beginning, and I think for the most part understood that different matrices, when I said that these all did the same transformation, they don't do it in terms of x's and y's. This stretches twice in the x direction, 4 times in the y direction. But there is a way of thinking about them where they do the same transformation. That is, they each stretch one of the eigenvectors by the factor of 2 and the other eigenvector by a factor of 4. So in that sense, they do the same transformation. And we can leverage that and take things that aren't quite as nice like this, and then do some of the calculations with a nice easy diagonal matrix. If you're just working with 2 by 2 and you're just finding one product with a vector, it's not that, it's a waste of time to do this, but we'll find that it's actually very nice when you're taking powers, and it gives us some tools to do other really nice things. So let's get down to here where the questions really started. So I had you do this thing. There was some confusion about why did I make such a big deal about this? You guys can easily do the multiplication here and get 6 and a negative 4. But I wanted to focus on the meaning of this. That meaning is, hey, there's 3 of this vector, which is kind of the x vector, and a minus 1 of the y vector. And the reason that this is so nice and so easy is because these happen to be the eigenvectors of this matrix. So we can just end up doubling how much of the first vector and 4 times how much of the second vector. So you get 6 and a negative 4. And we can do the same thing with vectors of other bases. So we're not going to think about this as 3 and a minus 1 like this. We're not thinking about it this way. With the standards basis, we're going to think about it in the eigenbasis of B, where this is 3 of the vectors that get doubled and a minus 1 of the vectors that get quadrupled. I had used a half and a half and a minus 1/2 and 1/2 here. I was just doing it really quick, and I knew those were eigenvectors, and I didn't have a chance to go back and refine this. But most of you just had 1, 1, a minus 1, and 1, which is fine. So I'll just work with that. It doesn't really matter because a product of an eigenvector is an eigenvector. So we can use whichever ones we want. So if I want to multiply this matrix by 3, 1, but that 3 and negative 1, but that 3 and negative 1 is in the eigenbasis of B, then that 3 and a negative 1 means this. It means 3 of the first and plus a minus 1 of the second. It doesn't mean this. It doesn't mean 3 in the x and a minus 1 in the y. And when I start calculating that, you might think, well, it's really hard. I'm like, you're making more work. Now we have to do more multiplications. And for 2 by 2, yeah, maybe it is more work. But notice, once we get to this point, this is easy because this is an eigenvector. That eigenvector is associated with lambda equals 2, so it just gets doubled. So this multiplication just becomes 2 times that. And this is the eigenvector associated with lambda equals 4. So this multiplication just becomes 4 times that vector. And if we want to keep our coordinates in our eigenbases, I just want to know how much of the first vector do I have? Well, I have 6 of those. And how much of the second eigenvector? Well, I have a negative 4 of those. So that's going to be the answer in in the eigenbasis. If I'm at a point that is 3 of the first eigenvector and a -1 of the second eigenvector, then when I do the multiplication, I'm going to end up at 6 of the first eigenvector and -4 of the second eigenvector. And this is just practicing doing that again with a different basis, with a different vector. I can't even remember with a different matrix, sorry. Can't remember what the matrix is. 4 - 2, 0, 2. And we're not going to go through it. So if this is in the eigenbasis of C, then, and we want something in the eigenbasis of C, we actually already know what this is going to be. It's going to be 6 and a -4, because this does the same transformation in terms of the eigenbases. It does the same stretching of the eigenvectors. Now, this isn't the same spot as the 3 and -1 up here, wherever that 3 and -1 is. That's not the same spot as the 3 -1 here, because they're in, like, it's not the same spot on the grid in terms of x and y's, but wherever it is, it does get stretched the same. So they don't start and end at the same spot, but the transformation that happens is the same. So look, I didn't even have to do that calculation. Oops. I didn't even have to do that calculation here because I could reason through what this was going to do. Oh, dang it, it looks like my word is stalling. It says look back at 5, use that to explain the shortcut for finding the calculation in A and B. Well, the idea is kind of what I just mentioned. Well, we know the transformation for each of these can be thought of as doubling the first eigenvector and quadrupling the second eigenvector. So since I knew that, I could just, and these were written in terms of eigenvectors, I knew what transformation I needed to do. I'd just double the first, multiply by 4 from the second. So all right. I think my word's coming back now. Okay, so the last few here is to try to put some of this all together to build up to this formula for similar matrices and diagonalizable matrices. So we're going to do a roundabout way, and the roundabout way, again, doesn't help if you're just working with a 2 by 2 with one multiplication, but if you're having to take a large power and do the product a whole bunch of times, it's worth doing the investment. So we're going to do a roundabout way to calculate our B-vet matrix times 3 and a -1. And again, it seems more tedious, but we'll be okay. The first thing we want to do, well, so this is in the standard basis right here, not in the eigenbasis. So we need to first translate it into the standard basis. So I'm sorry, to the eigenbasis for B to make it easy, so we can just do the scaling. So these were 2 eigenvectors. And so I need to know how much of the first and how much of the second to get 3, 1 in the standard basis. So these are standard basis things. We're using the language of the standard basis here. So C and D, what do I need? Well, I can think about that in different ways. I can think about that as 1, 1, -1, 1, 3 -1, and I can row reduce and solve. Or I can think about it as 1, 1, -1, 1 times CD equals 3 and -1. So if I think about it this way, then I can find the inverse matrix of this. So then I know the CD vector is going to be 1 -1, 1, 1 inverse, 3 and -1. It ends up being 1, 2, I think. 1 and a -2, maybe. So it's only because I've done this before that I get the 1 and a -2. But we can double check really fast that if I take 1 of the first vector minus 2 of the second vector, well, 1 times 1 is 1, and then I get a +2, so that gives me 3. in the first row. Second row I get 1 minus 2, which is minus 1, so I'm good. Yeah, so I quickly just calculated the inverse of this with a 2 by 2 because it has a nice formula, multiplied it by that, and that's what I got. Okay, so now 1 and minus 2 I think of as this is the, it's the same coordinate as 3 and minus 1, except this is in xy coordinates, and this is in the basis vectors for B. So if I come up to one of these, so here's xy's, okay, so 3, negative 1 is right there. That's 3 and negative 1 in the standard basis. But how about B has a basis, those basis vectors look like this. And we said that 1 and negative 2, that's the same spot as 3 and minus 1 in the standard basis. So is it true if we take one of the first, and we have 1, 1, this one is the first one, and a minus 1, 1 is the second one. So if we take one of the 1 1s and a negative 2 of the minus 1 1s, do we end up in the same spot? Well, if we take one of the ones, we're right here already, and then we take opposite of that direction of the second one twice, and there we are. We end up in the same spot. That gives us the same spot, but we're dealing it with coordinates of this kind of v basis, the two vectors to make the v there, and not our usual xy. But that makes it easy for us because now we can just do some easy scaling. Okay, we're not quite to the scaling yet. So, but that's what that represents. Okay, so we have the same point, but we're representing it in terms of how many of the first eigenbasis, how many of the first eigenvector, how many of the second eigenvector. Great. This is just the point that I already made up here, that if we take this matrix, notice this matrix is, this is a matrix of eigenvectors. This is the eigenvectors of B, and so we have the first and the second one, and what we did was we found the inverse of that matrix, P, and then we and multiplied it by this vector, 3 and minus 1, to get our coordinates in B. So we'll come back to this idea. So, but this is the first place we see this inverse coming up. We have a matrix here that we'll end up calling P, and it's our eigenvectors, and then we have the inverse matrix, and we use that inverse matrix to transform from standard basis to coordinates in the eigenbasis. Okay, so so now that we have our coordinates, now that we have our coordinates in our eigenbasis, the scaling is easy. We can just use this. We know that it stretches 2 in the first direction. It doubles the first eigenvector, and it quadruples the second eigenvector. And if we're at 1 of the first eigenvectors, we're going to end up with 2 of the first eigenvectors. And if we're at negative 2 of the second eigenvectors, multiply that by 4, we're going to have a negative 8 of those eigenvectors. So, but now we wanted to go back to the standard basis. So that's still in eigenbasis coordinates. So this is a kind of like in the B coordinates. So what about getting it back into the standard basis? Because we started with a standard basis. We want to end with a standard basis. So, so now we need to, when we think about this, okay, if I have 2, just the meaning of this in basis means that I have 2 of 1 1s and a negative 8 of minus 1 1s, because these are my eigenvectors. These are the basis vectors that I've been using. And so then I can do that computation, and that's 2 minus 8, which is a negative 6, and this is 2, that's minus a negative, minus a negative 1, so that's going to be 10, and then that's going to be a negative 6. And that's one way I could do it. I can also represent this as a matrix multiplication. Okay, and so here I'm back to that matrix P. So to get into the standard basis, I multiply the coordinates in the eigenbasis times the matrix that it has the eigenvectors that's made up of the eigenvectors. And notice the order matters here. We just have to make sure the two things that we have, make sure it's in the first row, and the -8 things that we have to make sure it's in the, sorry, I said first row, I mean first column. The -8 is the negative of the second vector, so that needs to go in the second column. Okay, so number 10, you probably noticed that going back to standard coordinates is easier than going from standard coordinates to eigencoordinates, because we already had these eigenvectors. We didn't have to solve for an inverse. Write down the process as a matrix multiplication using the matrix P from the problem above. That's what I did up here. So P times 2 and -8 equals 10 and -6. Okay, so, or even just, you didn't have to write P, the 1 minus 1, 1, 1 would work. Okay, so now we found a whole roundabout way of calculating this. So B times 3 minus 1, and B was just 3 a minus 1, a minus 1, 3, so I could rewrite it this. That's the same as, well, what did we do first? Well, we started off by multiplying this by the inverse matrix, 1 a minus 1, 1 of our eigenvectors, and then we scaled it. After we did that multiplication, then we scaled it 2 in the first eigenvector direction, 4 in the second eigenvector direction. And then we converted it back to the standard basis with this. So this is P, this was our A, this is P inverse, and this is our, it was the vector we were using. But the point is that this B times 3 and a minus 1 is the same as all of that times 3 and a minus 1. So B is equal to PA P inverse. And in doing this process, we've learned a lot about what P and P inverse are. P is a matrix with columns as eigenvectors of B, and then P would be the inverse of P inverse is the inverse of P, and we can also add meaning. So this converts our standard basis vectors in the standard basis to vectors in an eigenbasis of B. Then A, hopefully it's a simple matrix, like a diagonal matrix, and then we can do the easy scaling in the eigendirections, in the directions of the eigenvectors, and then we can go back to the standard basis with P. So that's the whole process that's taking on. So this is where the idea of similar matrices comes in. That's the formula for similar matrices. So it's right there. Okay, so let's use this where it's not just extra tedious work, but you can see the power of this happening. So here's a simple population model of rabbits and foxes. This problem was actually on the midterm exam last semester, although we didn't do 15. I think we did 6. So if we're starting off with 1 rabbit unit, maybe that's 1,000, 1,000, and 2 foxes, maybe that's 200 foxes or 20 foxes or something. I'm just not worried about those units right now. What's the population in 15 years? So notice that the more foxes there are, the larger the decrease in the rabbit population. So so if there's too many foxes, they might eat all the rabbits. That's what this model shows. So what we're going to do is, first we're going to find the let's find the eigenvectors and eigenvalues here of that matrix. I've already done this. So, well, the eigenvalues are just right there because it's a triangular matrix. Lambda equals 1.5, lambda equals 1.1. And the eigenvector associated with lambda equals 1.5 is 1, 0. And the eigenvector associated with 1.1 is 1, 4. Okay, so now I can think about this matrix 1.5, 0, minus 1, 1.1. I can think about this matrix as I'm going to write this diagonal matrix first. So I'm going to make this diagonal matrix where this is the diagonal matrix with made with our eigenvalues. And I have two linearly independent eigenvectors, so I can put them in our P matrix here. Now, why did I put the 1, 0 here and the 1, 4 there? How come I didn't switch them? It's only because I put I want to just match up. Oops. That's 1.5 is in the first column, and I need to put the eigenvector that it's associated with in the first column. And this 1.1 is in the second column, so I put the eigenvector it's associated with in the second column. So I'm just matching those up. And then I find the inverse of this, and the inverse of P here. So I need P inverse. And since this is a 2 by 2, I can rewrite that as 4, 1, 0, minus 1. So I swap the downward diagonal, swap signs in the upward diagonal, but then I have to divide by the determinant. The determinant here is 4 minus 0. It's 1/4. So there's P inverse. And now why did I do all that? Well, I need to figure out what 1.5 a minus 0.1, 1.1 0 is to the 15th power times 1, 2. So that's our initial population, actually to the 14th power. If I want to find it in year 15, oh no, in 15 years. So we'll do 15 there. If it said in year 15, then it would be 14 more years. But that's hard. That's going to take a long time. But that's the same as 1, 0, 1, 4, 1.5, 0, 0, 1.1. And I'll rewrite this as 1 minus 1/4, 0, 1/4, 1, 2, with all of this as this to the 15th, which looks more complicated. But this right side is easier to calculate because when we start multiplying all these three matrices together, I'll just write PA, P inverse, PA, P inverse, PA, P inverse, etc. Like this P and this P inverse, wherever they're multiplied together, they will become the identity matrix. So you get this thing, and so that matrix is just raised. That A matrix is raised to however many powers we raised the triple product to, which is just 15. So I get P times A to the 15th. And since that's a diagonal matrix, that's easy. I can just distribute it into each of the diagonal entries. So this becomes 1, 1, 0, 4, 1.5 to the 15th, 1.1 to the 15th, 1 minus 1/4, 0, 1/4, 1, 2. And so now I can actually start multiplying over here. So if I do this thing, this product, I get 1 times the 1 2 times the minus 1/4, which is minus a half, so I get a half. Oops. No, I did want that there. 1/2, and then I get 0 plus a half, so I get a half. So this is my, this was in the rabbits and foxes. It's kind of my standard basis now. This is rabbits and foxes. But now I'm in eigenvectors. So this is like how many of the eigenvector 1, how many in eigenvector 2 that I have. And now I can multiply that by this. Now I can multiply it by that transformation matrix, such that this 1/2 will be multiplied by 1.5 to the 15, and this 1/2 will be multiplied by 1.1 to the 15, and now I have a new vector, and I just multiply that by 1104. So this is in this is the stretching in the eigenvectors positions, the eigen things. I think I missed. Nope, I'm good. Okay. So now I do this to, because this is in the eigenbasis, and not the rabbit-fox basis, but I want to get it back to rabbits and foxes, so that's what this is. This first one will tell me how many 1 zeros I have. The second one will tell me how many 1 4 combinations I have, and then it'll get me back into rabbits and foxes. So I end up with just, the first one won't change, 1/2 times 1.5 to the 15th, and then the first one does change. So that's the 1 times that plus 1 of the foxes, 1/2, 1.1 to the 15th, and then I get 4 of the denominator, 4 1/2s, 1.1s to the 15th. So there we go. Although it seems like that should be negative somewhere. I don't know if I missed a sign somewhere. But anyway, you get the point. So this would give me population of rabbits and foxes 15 years later, which is a lot easier than trying to multiply this thing by itself 15 times and then multiplying that by 1, 2. Okay. All right. Hope that helps out. Again, thanks for your patience yesterday when it hurt to talk.